Hi everyone, we're continuing with Lesson 18 on binomial distributions. So far, we've talked about three binomial experiments that give rise to three different binomial distributions. These are distributions for x, a binomial random variable, which counts successes. So in the Monty Hall problem, we had students in teams play 18 rounds of the Monty Hall game. X counted the number of successes among those 18 rounds. And it turned out that X had a binomial distribution where N, the number of trials or rounds, was 18, and P, the success probability per round, was, perhaps surprisingly, 2/3, not 1/2. And we saw that this distribution in tabular form looked like this. X, the number of wins, went from 0 to 18, and here are the corresponding probabilities, with a peak at 12. Now, this is a binomial distribution because we have a fixed number of independent trials, n equals 18, and what happens in one round does not impact another round. Each trial results in a success or a failure. A success means, of course, you win the car. A failure means you win the goat. And the success probability is fixed. It's 2/3, and it does not change from trial to trial, from round to round. Now, I also mentioned a coin experiment. Let's look at the Rossmann chance applet. Let's say we have a fair coin where the probability of heads is 0.5, and let's say that a success is heads, not tails. Although remember, something like a death could be a success. Here, a success is heads. Let's say that the coin is flipped 100 times. Okay, so this student gets 54 heads and 46 tails. You see the little dot there on the 54. It's a dot plot. You see the dot there for 54. Okay, now let's say that we repeat this 1,000 more times. 1,000 more students flip the coin 100 times. So for the 1,001 students, this is the frequency histogram for the number of heads. The binomial histogram, where n equals 100, I'll bring this up here, where n equals 100, and p equals 1/2 or 0.5. The binomial distribution where n is 100 and p is 1/2 or 0.5. The histogram is in green over here, and it closely matches what we see from the frequency histogram. Okay, so again, in this coin experiment, we're seeing a binomial distribution for x, the number of heads. And this is, in green, a frequency distribution for x. Okay, so why do we have a binomial experiment in the coin situation? Because again, we have a fixed number of independent trials, n equals 100. Each trial results in a success or a failure. A success means a head, a failure means a tail. And for each trial, there is a fixed probability of success. For a fair coin, p equals 1/2, and that does not change. The coin is not made of bread. P stays at 1/2. It's made of solid metal. Okay, p is 1/2, q is 1/2. So in the coin situation, if x is the number of heads, the number of successes, then x has, as its distribution, a binomial distribution where n, the number of trials, is 100, and p, the success probability per trial, is 1/2 or 0.5, the probability of heads. Now, in the dice situation, this is where we're rolling a die 5 times, or we're rolling 5 dice, and x is counting the number of 4s that we get. Well, n equals 5 is the number of dice that we roll. A success means you get a 4. A failure means you don't. We have a fixed probability of success. It's 1/6. That's the probability of getting a 4. The probability of not getting a 4 is 5/6. So in our dice example, if x is the number of successes, the number of 4s among the 5 trials, or dice, then X has a binomial probability distribution. X is binomially distributed where n is 5 and p is 1/6. N and p are the parameters for this distribution. If you change one of them, you change the distribution. If you change the number of dice, if you change the probability of a 4, then that changes the distribution. It turns out that the distribution table for this binomial distribution is this. Of course, we can get between 0 and 5 fours among the 5 dice. The probability of getting no fours is about 40%. Coincidentally, the probability of getting 1 4 among the 5 dice is the same, about 40%. The probability of getting all fours on the 5 dice is almost 0. It's not quite 0, so we put 0 plus, because it's very powerful to say that something's impossible. It's not impossible to get 5 fours on the 5 dice, but it's pretty close to 0. It's 0 to 3 decimal places. In fact, the probability of getting 5 fours on the 5 dice is about 0.000129. It's very close to 0. Okay, now, again, this is a dice scenario where we're counting the number of fours among 5 dice, or among 5 die rolls. But there are other binomial experiments that give rise to this distribution. Going up the notes here, similar examples. Let's say that 1/6 of all Americans have cooties, this disease. We randomly sample 5 Americans. Now, I know that technically we have dependence here, but by the sampling rule, we can assume independence. The probability we get the same person twice by chance is minute. Let X be the number of Americans in the sample with cooties. So we have a binomial experiment here because we have independence. We have 5 trials, the 5 Americans. Each trial ends up in a success or a failure. Here, a success means you have cooties, so you may not want to be successful. And the success probability, 1/6, is the same for all 5 Americans. Again, we're assuming independence under the sampling rule. Let X be the number of Americans in the sample with cooties, and lo and behold, it's the same distribution. It's a binomial distribution where n, the number of trials, is 5, and the success probability, the probability that a given person, American, has cooties, is 1/6. And the binomial distribution looks like this. There's about a 40% chance that nobody among the 5 Americans has cooties, about a 40% chance that 1 American among the 5 has cooties, and so on. Another experiment that gives rise to the same distribution, a multiple choice test has 5 questions, so n equals 5. Each with options A through F. That's 6 possible options. A student guesses randomly on all 5 questions. So the success probability per question is 1/6. On any given question, there are 6 possible options, A through F. The student guesses randomly. There's a 1 in 6 chance that the student gets the question correct. Let X be the number of correct answers or responses. So on a test with 5 questions, X could be between 0 and 5. Okay, X counts the number of successes, and again, it has the same binomial distribution we've discussed. N equals 5 trials or questions, P equals 1/6, the shared probability of success. In this case, the student guesses randomly. On any given question, 6 options, P is 1/6. So in all 3 of these cases, actually, now it's 5 examples where we have a binomial experiment. I just described 3 experiments where we have the same binomial distribution. We roll 5 dice and we count the number of fours. X, the number of fours we get, has a binomial distribution, n equals 5, p equals 1/6. In the cooties example, n equals 5 Americans, that's the number of people in our sample, the sample size, 1/6, that's the probability that any given American has cooties. On this multiple choice test, n equals 5 questions, P equals 1/6, because each question has 6 options and the student guesses randomly. So for this student, the probability the student gets no questions correct, all wrong, is about 40%. The probability the student gets exactly 1 question correct turns out to be the same, about 40%, and there's almost no chance that the student gets all 5 questions correct. It's this over here. Okay, so we'll continue with this in the next lesson.